Login accepted.
So, hello everyone. I think we can start. Take your seats. I hope you are not mistaken with the session. Is it really what you wanted to hear about? Sonar, Kotlin? So it was your last chance to leave. So now you stay here. So today we're going to talk about SonarKotlin, a better static code analysis tool for Kotlin. So please raise your hands if you use Sonar products, like SonarKube, SonarCloud. OK, and raise your hands if you're using Kotlin and Sonar products. 2 people. OK, so only 2 people would like to hit me today. That's a joke. I hope it won't be like this. So before we start, let me introduce myself. My name is Margarita. I work as software engineer at SonarSource, or you can call it Sonar now. I like conferences. I'm a frequent speaker. Okay, if we delete all, like recently 3 years of pandemic where there were no offline conferences, but I like to speak at them. I also organize them in my home city in Kyiv. And I also like a lot of different programming languages like Java, Kotlin, Scala, TypeScript, and so on. So I probably tried most of them on backend and sometimes on the front end and in writing different stuff. This is my Twitter handle. You can follow me if you want. I sometimes tweet interesting things. And another thing that I'm working at SonarSource now, and this company is based in Geneva. And so I came from Switzerland. Switzerland is famous for its Swiss chocolate, so I brought you some of Swiss chocolate. I was told that it's the one that you cannot find in Poland. So maybe after the talk, you can taste it and say me whether the Swiss chocolate is as good as it is advertised. And usually when introducing myself, I used to tell that I actually do a lot of boxing and be like, you don't need to joke with me. But today I'm not going to do this joke. Today I have another slide for you. As I already told you, I'm originally from Kyiv. I was born in Kyiv and I was raised in Kyiv, and I'm only 2 years in Switzerland. And today my country is struggling. You know, there is a real war. People are being killed, raped, and tortured. And I know how much Poland helps. I'm really thankful all Polish people for all your hostility and how you for your donations. And this is just a slide to remind you that there is still a war not far away from this place, and we still need your help. We need your presence there. So let's start. Short disclaimer. What I'm going to talk about is just my opinion. You can see that I'm not using SonarSource theme. I'm using my own theme. That means that my employer has nothing to do with this presentation. It's just my own opinions. And another disclaimer. Today, I'm not going to sell you Sonar or SonarKotlin because it's not my job. My job is, I'm a developer. My job is to write code. I'm not going to explain you how to use our products because there are a lot of nice perfect tutorials how to use our products. And it's also not my job to explain people how to use our products. So today, I'll explain you why we needed to do something with our Kotlin analyzer and actually how we did it. So in order to be on the same page, there will be a few terms that I will use during the presentation that are somehow referencing like compiler constructions and so on. I won't give you the complete course because it's coming from university, it's hard, and probably most of you know some of this. But let me just remind you. First of all, it's abstract syntax tree, or just syntax tree. It's your source code can be represented as a data structure. This data structure is a tree. For example, you can think about your files as a root node. These files your file could have some child nodes like classes. Your classes could have child nodes like functions, fields, so on. And you might have some leaves. Leaves is just nodes without children. So it could be statements or something like final, which is very small, and it's just a leaf. Okay. Another term is semantic. Abstract syntax tree is about syntax. It's just about that this is a function, this is a class, this is their name, and identifiers, and so on. A semantic is something that contains additional information. Semantic contains information about types, references, and some other relations between different AST nodes. We will look a little bit deeper into semantic further in this presentation, so if it's not clear for you now, it probably will be clear for you a little bit later. And the last term is compiler frontend. When there is frontend, there probably is backend, and you're right. Compiler, in simple words, contains like two different paths. First one is a compiler frontend. It takes your source code and generates abstract syntax tree and semantic. And backend takes your syntax tree and semantic and generates bytecode or generates machine code. And this is like two paths. Today we're not going to talk about backend. Today we're going to talk about frontend. And this is what actually frontend is the function from source code that generates AST and semantic. And here it is, agenda. And so today we'll talk about the history. What were the preconditions at Sonar Source and why we had to do some things with SonarKotlin, what it was and how it became today. We'll talk about the challenges that we faced, so you'll be able to understand why our analyzer behaves this or that way. We'll talk about the achievements, because, okay, we spent some time, we spent some manpower, you probably achieved something. And there will be some takeaways, the things that you can take from this presentation and maybe apply to your everyday job. So this is how the SonarKotlin 1.8 and the report using this analyzer looked, for example, in SonarKube LTS version. It was like before we started working with this. You can see, for example, there are 64 bugs, there are some security hotspots, no vulnerabilities, some code smells, and actually 4 days of technical debt. So SonarKube tells you that in 4 days, you can make this project perfect. And this is how exactly the same project and report looks in SonarKotlin 2.9. Actually, it's the latest available, which is probably available in Sonar Cloud, and probably will be available in the latest SonarKube. You see that there are 3 times more bugs. There are 200 vulnerabilities, while there were 0 vulnerabilities. There are 800 code smells, and almost a month of technical debt. So SonarKotlin 2.9 tells you that you need 29 days to actually fix everything and to make your project perfect. So does it mean that our job to make your project worse? Okay, of course not, but our job is to find more. And you can see that SonarKotlin 1.8 could be able to find less bugs, less code smells, and that's why it showed you less technical debt. And we are able to show you more in SonarKotlin 2.9. In order to understand what was SonarKotlin 1.8, let's use our time machine and go a little bit to the past. SonarKotlin 1.8 had 40-some general rules. General, it means like bad function name, too long function, and so on. Low rules precision. There were a lot of corner cases that were ignored. Import of external linters was outdated. So probably Detect or Android lint, they evolved for a few years, but it wasn't applied to, and wasn't represented in our SonarKotlin. And unfortunately, it was hard to maintain, hard to debug, hard to extend, and this analyzer had no future. In order to understand why it happened, why it was like this, let's go even more in the past and look at the brief history. Some years ago, in Sonar Source, there was an idea that we need one ring to rule them all. What do I mean? When we're talking about analyzer, there is, in a very high-level overview, there is this path. First of all, you give us your source code. Then we generate abstract syntax tree. And then we run our checks, rules, and our analyzers, and provide you the result. What's the problem? The problem that each language is different. Each language has different syntax, different language structures, and it means that every AST is different. So we cannot write one check and it will be available for every language. We need to duplicate, for example, if we support 27 languages, we need to write one check, like bad class name, 27 times for different ASTs. And that looked like something not really optimal. So the idea was to have some general AST, to convert the language-specific AST into something general, then run analyzer on this general AST and generate the result. And actually, it was implemented. Thank God it was not implemented for all 27 languages, just for these 4. And this technology called Slang, and the AST was Slang AST. There were 4 languages that were written on top of this engine: Kotlin, Scala, Go, and Ruby. And let's look at some pros and cons of such approach. And you can actually see that this is open source. So if you haven't heard about this, you can find this project, look at this, and if you need some basic support for some new language, it's a good way to start. So, pros. First of all, you write one rule, and it's available immediately in many languages, like in these 4 languages. Then, if you need one language, you just need to write a converter to this general AST, and you have all the rules that are immediately available for your new language. And that's it about pros. About cons. The maintenance was hard because, okay, there are 4 different plugins, there are 4 different languages, and sometimes the change in one language could cause the change in Slang AST, and it means the change in all 3 other languages. So maintenance was really costly. Rules precision. Rules precision was also not that good because when we are talking about something general, when we have 4 different languages and we try to convert them to some unified representation, we have to cut some branches. There were, for example, no such place for extension functions or some other Kotlin constructions, and Ruby constructions and specific Scala constructions, and that means that this analyzer will never report anything for these constructions. Another problem is language-specific rules. As every language has some specific syntax, specific constructions, it will be nice to have some rules. But it was really hard to write rules that only was for one language, but not for 3 others. Testing was hard, because now you have to test the rule 5 times, 1 for Slang and 4 times for every language. And there were no place for semantic. And actually, no place for semantic was one of the biggest problems for Kotlin. So this is general Slang pros and cons. Let's talk about the trade-offs that we had while using Slang for Kotlin. First of all, unsupported features. As I already told you, extension functions, objects, anonymous, and so on. It was not supported, so nothing will be reported for this. Just syntax. So there were no place for semantic. It means that we can only report if your structure of the code is wrong, or nice, not nice, or if your names are not, or line length is not correct. But that's not enough. That's not advanced bugs, so it was not really that cool. But there was one good point. It was fast. Because as we don't need semantic, it was really fast, and our users were really happy to have the fast analysis. And there were no dependency on the class path. If you're using Sonar products and you're using Java, you know that if you not compile your code, the result of analysis will be less, spoiled a little bit, because we need some semantic information. And we need also your class path, and if you don't give us the parameter of your libraries and dependencies, the result will also be not that good. And if we want to make Kotlin as good as Java, or even better, we also need this class path. And that was time to think about SonarKotlin 2.0, because in different places, and PMs, both the developers, we wanted to use Kotlin, we wanted to have nice analysis for Kotlin, and we wanted to rethink what we provide to our users for Kotlin. And this is how the idea of SonarKotlin 2.0 began. Challenges. what we faced on our way. We thought it would be much easier, but unfortunately, we faced a lot of them. The first challenge was how to start. It's usually easy to start the project from scratch, like when you have nothing. You can do whatever you want, and you can create some plan and so on. For Kotlin, the situation was different. We already had some Kotlin analysis. We already had an analyzer. We already had some working project. And for some reason, we needed to substitute it, or maybe write on top, or do something new on top of existing one. So how to start? How it was before. As I already told you, we had this general AST Slang, and the scheme was on a very high-level overview looked like this. You have source code, the compiler frontend generates Kotlin AST, then it's converted to Slang AST, Slang analyzer runs, and you have a result. This is how it worked. And this is what we wanted. We wanted to actually use native Kotlin AST. We already have it in the pipeline. We just wanted to use it for our checks. So this is the ideal world. Unfortunately, to understand what are the price of such solution, we need to understand what is the result. The result is actually 40 Slang rules. It means that already in the analyzer there were 40 rules that were working. And we cannot simply delete them, remove them, because our customers won't be happy. Imagine that in one version of analyzer you had some 40 rules, you had some issues with these rules, and you update it, or if you are using SonarKotlin, you just get it one day, and these 40 rules disappeared. So it would be strange, and I believe that people won't be really happy. Metrics. Metrics were already calculated based on Slang analyzer, and that was also something that we couldn't easily remove. So we need somehow to live with it. Native Kotlin rules. It is the part of the result that we wanted to add. It's actually the new one. And external issues. I mean the issues you import when you're using Detect or Android lint or any other external linter. So the thing is, we cannot easily remove Slang. We need somehow to live with it. So we were thinking what to do, how much time to spend, and what actually we implemented. It was our first iteration. So we decided that, OK, for now, we leave Slang as it is. So 40 rules are based on Slang, metrics are based on Slang, and so on. But we'll write one more path that is based on Kotlin AST, and we'll write new rules based on the native Kotlin AST, not Slang one. So now the result is containing two paths. So there are two paths that leads you to the result. One is based on a Kotlin AST, another one based on a Slang AST. So it doesn't look really nice. It doesn't look like something that we wanted. So we decided to mark the Slang as a technical debt and promise ourselves that eventually we'll get rid of this. That's actually was our first iteration. So Kotlin AST. I'm talking a lot about Kotlin AST, but actually what it is, what's under the hood. There were different variants that we can took as our AST. First of all, it's program structure interface. If you ever wrote some plugin for IntelliJ or any other IDE based on IntelliJ, you probably heard about this. This is an interface for adding the support of new languages in IDE. And Kotlin initially was implemented as an implementation of this program structure interface. So Kotlin compiler depended on this, and this is something that we already used in Slang. Another possibility was front-end intermediate representation. If you heard about K2 compiler in Kotlin 1.7, it's about this. And you probably heard that in 1.7, it's in alpha stage. So front-end intermediate representation is not yet ready for production, so it has better API. It is the future of Kotlin compiler, but we cannot use it right now. And another solution could be unified AST. This is actually an open source project. It generates unified AST view for Java and Kotlin. But unfortunately, it has worse precision because it's unified view. And this one is used in Android lint. So maybe because of this, you can understand why Android lint behaves this or that way. So we generated some kind of this decision-making table and decided that we'll go with PSI, our Program Structure Interface, PSI. But it comes with some trade-offs. First of all, it's a nullability hell. What do I mean? Imagine like this kind of code that we have, for example, for binary expression. If we want to implement such check, we want to visit binary expression. You can see that right expression and left expression are nullable. Why? Because Kotlin compiler should provide some error recovery. Sometimes, if code was not parsed correctly, if you're, for example, just typing it, or if you have some problem, some error in your code, it might be possible that KT binary expression might not contain right or left elements. But in our case, in case of analyzer, if code was not parsed correctly, currently we are not running analysis on this. So if parsing was wrong, we will never run it. So it means that in our exact case, right and left are always present. But unfortunately, because it's nullable and nullability is embedded in type system in Kotlin, we have to deal somehow with this. So the first idea was to use somehow safe dot with functions like let, apply with. It works, but it provides useless nested levels. And if you have just 2 of them, okay, you can live with this. But if you, for example, have 5, 10, or even more of nested level, which is useless, it doesn't really look nice, and it spoils the readability of your code. So nesting is a big problem here. What else we can do? We can use Elvis operator and, for example, return. It works. It's okay. It looks nicer. It doesn't have this nesting. But the problem is that we still have unreachable paths, because technically, according to like compile time, it's reachable. But in our context, we cannot ever go to this branch. And it means that when we run JCoco or any other coverage tool, it tells us that you have unreachable branch and you can do nothing with this. So in some cases, we actually use this approach, but we tried to seek something better. Another solution could be just to use this non-null assertion. Because, okay, we are sure that in this case, we will never face null pointer exception. But every time I am putting this non-null assertion, something inside my stomach telling me that, okay, maybe you're wrong, maybe you should not do this. I don't know from where it's coming, but every time I believe it's tricky. So after a lot of holy wars and talking in my team, we decided that, okay, we'll leave it as is, but we'll put some comments. So every time we put a non-null assertion, we leave a comment why we decided to put it there. Because if our assumption was wrong, we can easily understand what was the assumption and fix it. So maybe you can use this trick as well. So another problem of program structure interface was IDE dependency. What am I talking about? Program structure interface is coming from IDE, and it means that Kotlin compiler had to embed some parts of IDE. Sounds scary. In Sonar source, we have our internal joke that we have IntelliJ. Probably most of you are using this. In IntelliJ, you can download plugin SonarLint. In SonarLint, there is a plugin SonarKotlin for Kotlin. SonarKotlin, we embed Kotlin compiler, and Kotlin compiler embeds IDE. And we need to go deeper. Yeah. So, of course, it's not embedding all the IDE, it embeds just parts, but the joke was nice. And another problem is naming. What is KT named function? Do you have any ideas what it is? Or maybe you just need to wake up after yesterday's party. So actually, I asked this question when we were recording the podcast with Hadi and Sebastian talking Kotlin, and I asked them, what is KT named function? 2 guys who are actually working at JetBrains or are familiar with Kotlin. And they assumed that it's a function with a name. Either did we. We assumed that KT named function is a function with a name. So when we implemented a rule, for example, that function name rule, what we did, we know that we are always compiled, so name should always exist. If it's KT named function, name is always present. And then we started testing this. we tested with, for example, anonymous function. It's possible to do in Kotlin anonymous function. Yes, it's possible. It's compiling, OK. What we thought, anonymous function is function without a name. So it shouldn't be KT named function, so we simply won't get into this method. So we run it, and we got null pointer exception. Why? Because function.name, we say that it's non-nullable, but unfortunately, it's null. Why it happens? Because actually, anonymous function is also a KT named function. After some investigation, some talks to with JetBrains guys, we realized that KT named function has nothing to do about the name of a function. It means function declared with keyword fun. And if you think that it's the only problem with naming is Kotlin compiler, you're wrong. There are a lot of gems like this, and OK, we have to deal with this. Another problem was zero range. Some time ago, we implemented the check with deprecated code used rule. We were a little bit cheaters. We didn't want to implement this rule on our own, so we just retranslated the warning from a compiler. It means that actually the reported element comes from a compiler. And it was OK, it worked. We faced no issues there. And at some point, one user complained with a test case, and here is some test case. Test case is enum. You have enum, you deprecate it, you have one entry there, and you get index out of bounds exception. Why? Because you actually try to report on something that has zero length. So something that does not actually exist in your source code. Here it is. So the reported element is somehow between the entry 1 and the opening bracket. So how SonarKotlin can report there? Like, there is no actually symbol there. And that's why we had this index out of bounds exception coming from SonarKube. So we realized that actually when you deprecate enum, you not only deprecate enum, you deprecate primary constructor. And when you do entry and opening bracket and put some argument there, you're calling this primary constructor. You are not doing it explicitly, you're doing it implicitly, but there is no explicit call to my enum class, but you are still calling primary constructor, and it's deprecated. So here is the warning. So we thought maybe we can filter out such cases or do something else, and we went to the IntelliJ. We see that IntelliJ actually reports opening bracket, and we decided, OK, if IntelliJ can report opening bracket, why couldn't we? So we are consistent, and we also report the opening bracket. So knowing all the problems with program structure interface, we still believe that someday front-end intermediate representation will be production ready, and we'll have to rewrite on front-end intermediate representation, which will fix a lot of problems with BSI. So that was just a lot about decisions, how to start. Let's talk a little bit about code and actual coding challenges. First of all, the big challenge was adding semantic. In order to understand deeper what semantic is and why do we need this, let's imagine some code, like this example. There are 6 different examples of calling random function from Java and Kotlin. What if we want to report on every Java util random call? Previously, if we don't have semantic, we can only report if it's code with fully qualified name, because fully qualified name contains Java util random. But if we have semantic, there is a possibility to report just random and resolve import, because import says you that you can use random without fully qualified name. Without semantic, we cannot map this random call with that import. So without semantic, we won't report this. And that's why we need it. Another example is let's report every Kotlin random function. So it's easier to report when it's, again, fully qualified name. But if you want to report a named import, you need semantic to resolve this named import. And the last example is let's report every Kotlin random function if it's called with 0. Again, if 0 is hard-coded, it's easy to report because it's hard-coded. Like you just need syntax for this. And if you want to report cases like this, to understand that x is actually a value, a final variable, and it's initialized with 0, you need semantic here as well. So with semantic, we can actually do such kinds of bug detections and even more. So why do we need semantic? To have better rules precision, to write more complicated rules, to write security rules, Android rules, and so on. So in order to provide a good number of rules, a good quality analysis for Kotlin, we need semantic. So how to do this? As I already told you, Kotlin compiler did not, Kotlin analyzer didn't depend on your dependencies and your class path. And now, if you want to have semantic, we need your class path. So if you are using Maven or Gradle plugin for SonarKotlin, it's done by default, so you don't need to do anything. But if you're using just Sonar Scanner, you need to pass class path in order to have these advanced rules in Kotlin. And then when you have class path and you have source files, we can generate binding context. Binding context is actually the structure with semantic coming from Kotlin compiler. And we need a bit of magic because, as you might know, as you might notice, that working with Kotlin compiler sometimes could not be easy. So we need some kind of magic. What is binding context? Binding context is a structure that is containing some slices. Slices like type, reference target, resolved calls, and so on. And each slice is actually a map. Map that contains some KT element, a node from your abstract syntax tree. And value could be other KT element, so it just tells you that this is references to this. It could be descriptor, some additional information, or even constant, because you can actually resolve some compile time constants using binding context. And in order to use it, you just, like in a simple map, you use method get, but as a first argument, you pass the name of the slice. And there are a lot of different slices, so sometimes we have to guess which slice is about what, because the documentation is sometimes not enough. But that's actually how we work with binding context. Of course, you can write some wrappers, some utils, some helper functions, but under the hood, they all go into binding context get method. So this was about semantic, and we implemented some rules with semantic. We implemented actually some bridge to use new Kotlin native tree. That was time to release. And in order to release, we wanted to actually get rid of being connected to Slang. Let's extract SonarKotlin in separate repository, because everything before this slide was done in actually Slang project. You remember this slide. We had some technical debt, and that was time to pay it. It was very boring, very uninteresting work, so I am not going to tell you like how we did it, because it's just simply to do it. But I'll share some things. What was actually the debt? Debt was 42 Slang rules. Before this, I told you that there were 40 rules, but while we tried to pay this debt, we actually calculated and find out that there are 42. We had some metrics in our debt that we need to rewrite to use new approach. We had tests, and we had a bridge to the new engine, because you remember this ugly scheme. So we rewrote 42 rules, we rewrote our tests, we rewrote metrics, and we removed this bridge because finally it was the only path. We got rid of the Slang. It was hard, it was painful, but we managed to do it. We expected that it would be something like this, like converting Java to Kotlin, because originally Slang is written in Java and SonarKotlin is written in Kotlin. But in reality, we faced like everything that could go wrong went wrong. We even faced GitHub outage there and problems with our CI. But finally, we did it. And SonarKotlin is there. Here is the project, so you can go there, give us a star, and waiting for your contributions. Here are some tips what helped us to actually pay this technical debt, because we know how painful it is. First of all, plan sprints for technical debt. In the very beginning, when we marked something as a technical debt, we not only marked them, we created tickets, we created some epics and so on, And we really saw how many tickets we should handle in order to pay this debt and how much time we need for this. Another tip is the sooner the better, because if you continue doing new work with debt, with a technical debt, it actually slows down your new work. So it's kind of harder. Once you pay everything, the development will be faster and development will be more pleasant to you. Gamification can help. In order to rewrite 42 rules, we actually had a bet with our manager, because he asked us if we can do it in like 4 days, to rewrite 42 rules in 4 days. And we managed to do this, and we won tequila, so it was a nice plan. And reward yourself, because sometimes it feels frustrating. When you're dealing with technical debt, it means that it will change something in code, you will change something for you, but it won't change anything for your customer. So nobody will see it as a result, and it could be frustrating. So reward yourself after paying technical debt, as we did with this tequila. And that was almost it. We were almost about to release the version of SonarKotlin, but we found out that when we were working on SonarKotlin, it eventually grew like drastically. For example, in SonarKotlin 1.8, we packaged using shadow jar, we used minimize, and we excluded some directories, and it cost us 8.5 megabytes, like the plugin weight. It was like more or less okay for our SonarKube, SonarCloud, and for SonarLint. So, okay, it was normal weight. But in SonarKotlin 2.0, when we started using semantics, started using binding context, we eventually had to comment out a lot of exclusions. Eventually, we got rid of minimize because it caused more problems than solved the problems. And we've managed to do this shadow jar with only 2 exclusions. And guess how big the plugin was? It was 60.5 megabytes, and we won a prize to be the biggest plugin in Sonar ecosystem. And the prize that we didn't really want. So we need to do something with this before release. So what we did, we played a lot with different possibilities, what we can do with exclusions, inclusions, with minimize or without. So we decided, finally, to go with minimize. So let's Gradle shadow jar to do everything for us and remove everything that's unused. But what was the problem with minimize? Unfortunately, there are a lot of classes that are removed by minimize, but are actually used and are dynamically loaded. And minimize cannot understand that we will actually need them. So they're removed, and in runtime, we don't have classes. That was said, and what we decided to do, we decided to do some trick. We actually named all the classes that we need, there were a lot, and put them into array. So by doing this, minimize wouldn't filter them out, and we'll still have these classes, but can still do its job and reduce the plugin size. So we got 33 megabytes. Okay, it's still not 8.5, but the plugin is harder and is doing more job than it was before. We talked to our SonarKube, SonarCloud, SonarLint teams. They told us that 33 megabytes is okay. Our C++ analyzer is almost like this. So we don't care. So we still think about how to reduce size, but the discussion is on hold. And we'll maybe do it in the future. So we did this trick, and prayed that anything would be broken, because who knows? So finally, SonarKotlin 2.0 was released. We expected something like this, but the reality was something like this. What actually happened? A few days after the release, when the plugin reached SonarCloud, we got a lot of user feedback that the performance drastically decreased, there are some out of memory, there are a lot of problems with performance and so on. And now, for example, if customer had its analysis running for 5 minutes, now it could be 2 hours, or even never finish at all. We were a little bit like surprised because we tested. We had some internal projects. We tested our analysis on this project, and we never noticed this drastically decrease of the performance. So we were a little bit upset, but we had to do something. So what we did, we gathered a meeting and said, okay, we need to improve the performance. Any ideas? There were a lot of brilliant ideas. Someone thought, let's use parallelization. Another said, okay, let's maybe do caching or incremental analysis. There was one guy who said, maybe let's find the bottleneck and fix it. Of course, we threw him out of the window. But actually, that was a nice idea to find the bottleneck. And the first candidate for the bottleneck was commented out code rule. After some investigation, we realized that for some reason, this rule is taken much longer than all other rules. So why? Let's consider the example. You have some example, you have some comments there. And if you take out comments from there, you can see that some of the comments actually look like code. For example, first and the last one. And two other comments doesn't actually look like code. So this check should actually report if you commented out the code, because it's something that you should eventually remove, like fix me or to do or something else. So we had a rule for this. How it actually worked? Worked like there is a comment body. We try to compile it using our Kotlin compiler frontend. And if it compiles correctly, it means that there is a code there, and we should report an issue. If there are some errors, it means there is no code there, and we should not report an issue. Sounds looks smart, looks like logically. What were the problems with this? First of all, before we used the semantic, it was fast. When we started using the semantic for compilation, the time drastically increased. And okay, we need to do it for all the comments there. So it's not just once per file, and if file, for example, has 500 comments, we need to do 500 times. And if you have 10 disk files, it's 5,000 times, and so on. So it could be exponentially, the time will exponentially increase. So the problem was with performance could be there. Another problem with this that, okay, when you're trying to compile something that could not actually be a code, you might face some compiler bugs that we faced because you're testing some corner cases. And actually, we faced some compiler bugs while working with this check. There could be code with mistakes. It means that it won't compile, but it's still code, and you probably want us to report it there. But this algorithm doesn't take this into consideration. And another problem was infix functions. Without the semantic, when you compile, actually every 3 words or more words in Kotlin have a meaning, because you might have infix functions and you might omit dots and brackets. And just 3 words could be a correct code in Kotlin. So you need somehow to detect whether it's just a sentence or a code, which makes us a little bit crazy working with this. So knowing all these problems, there was an idea how to fix it. We decided, some of us decided that let's comment out the commented out code rule. We thought that, okay, that's a crazy idea. We'll have a lot of complaints and so on. But complaints of the performance were even more, so we decided to do this. And we had 0 complaints about this rule, so you can imagine how useful it was. So currently, this rule is not working. So if you're using SonarKotlin and you don't see any issues with commented code, it's just because there is no implementation for this rule. Okay, and the last one was about the performance. Because sometime we managed to improve the performance for some our users with commented out code rule. But some of them were still facing the performance degradation. In order to investigate it more, we need more input from our users. And usually, dialogue with users in our community forum looks like this. We want fast Kotlin analyzer. Can you please provide some logs? No. So we have to do something like magicians to try to predict what actually happened on their side. Having no source code, having no logs, no thread dumps, heap dumps, like nothing. Just a report of a person who is not happy. So we were doing some kind of guessing, and eventually one nice guy from the community provided us thread dumps. After looking for a long time into thread dumps, reading them, reading the reports, we realized that there is one common problem. It's binding context. It's not actually working with binding context, it's generating binding context. And we started to think and investigate what's binding context. In order to generate it, you need your source file and you need class path. Source file in your project, in your module, could be like not infinite number, but could be very big number. For class path, for one module, it's always the same. What we did, we generated binding context per every file. So if in your module you have 500 files, we'll generate binding context 500 times, going through all your class paths 500 times, knowing the class path is the same. Yeah, class path is constant, yeah. And the bigger class path is, the more time it is to parse it and to generate binding context. And big class path plus many times, it's time close to infinite in terms that it will rather reach the timeout than actually finish its work. So big class path plus many files, bad situation. And nice finding that Android and big private projects of Android, okay, I'm not sure if it's all projects, but at least projects of our customers are like this. Big class path, many files in a single module. And it means that for them, the time was like drastically, the performance drastically decreased. Why we haven't like noticed this in our code base? Because for some reason, like we tested with projects that were nicely modularized. So we never faced this problem because the class path was like comparably small and modules didn't contain too much files. And we had no access to some private Android projects, so we were able to test only some open source Android projects, and that were not that big. So we could not find this performance degradation on small projects. So knowing all this, we knew how to fix it, because let's just generate binding context once, and we were able to improve their performance. And this is actually the statistics from SonarKotlin. One is from the version before the fix, another one after the fix. So you can see that the majority of projects are now like around 200 seconds. It's big projects. And before it was much bigger, and some projects could like take almost 5,000 seconds to finish. So now it's much less. And we had some happy users. So once you start working on performance, it's hard to finish. So we also added more test projects, including Android, in order to be able to find this performance or other performance degradation in the future. We added performance measures, so in order to understand if we are having this degradation per each release. And we also find some slowest rules and optimize them. So now the performance should be even better than it was. So that's it for the challenges, achievements. In SonarKotlin 1.8, it was like this. In SonarKotlin 2.9, we actually had 98 rules, good rules precision. We updated all the external linters, and actually we made it a process, made it the default process of our releasing. So every time we release a new version, the external linters are updated. And yeah, and we see the bright future because now we have a semantic. Now we don't have old slang. So we can do whatever we want. We can do like something like advanced rules. We can do detection as Java does. So we see the future, the bright future of SonarKotlin. And how we did it? We used Kotlin native tree. We added semantic. We had security rules. We had rules for coroutines. We also implemented some rules for regular expressions. And we updated external linters and also added the support of KT-lint. And improved the community support. If before we started working at Kotlin, you might like wait a couple of weeks or even a month for your answer in the community, today it should be like in a day or a few days. Takeaways. There are a few things that I want you to take from the presentation. First of all, know your customers. You see that we failed because we didn't know how big Android project works, and we were not able to test on them. Then know your third parties. We were using Kotlin compiler, and we should master Kotlin compiler in order to use it correctly, not to face problems with it. release often, as we managed to release like every month, and by doing this, we were able to get the user feedback pretty fast and to fix problems. Refactor and rewrite. By removing slang dependency and rewriting it, you not actually converted Java code to Kotlin, you also fixed a lot of problems in the old code that we found out and a lot of stupid stuff that was there. So before we end, I would like to say some special thanks, because it was not just me working on Kotlin Analyzer. I had a dream team, Johan and Evgeny, who worked with me on this project. And special thanks to you for coming here, for sitting the whole presentation. Hope it was interesting for you. And we have no time left, but if you have any questions, please come here, and you have Swiss chocolate here, so we can talk. That's it.